In chapter 3, gas power cycles, we have already looked into the topic on analysis of power cycle, and then we look into the Carnot cycle and its value in engineering. So we also continue on air standard assumptions. There are few assumptions that you need to be able to understand, and I would highly recommend you to memorize the standard air assumptions, so that whenever you come across any problems in gas power cycle, you can then apply all the air standard assumptions with reasoning, right? And then before we had our break just now, we have already looked into an overview of reciprocating engine. Okay, from there we learn a few terminology that is very important for us to apply in the following subtopic, right? So next we want to go into Otto cycle. This is an Otto cycle, the ideal cycle for spark ignition engines. Okay, the Otto cycle is the ideal cycle for spark ignition reciprocating engine. It is named after Nicholas A. Otto, who built a successful four-stroke engine in 1876 in Germany using the cycle proposed by Frenchman Beau de Rocas in 1862. So this guy, Mr. Rocas, already proposed the cycle in 1862. However, Mr. Otto successfully made it realistic in 1876. Basically, in most spark ignition engine, the piston executes 4 complete strokes, 2 mechanical cycles within the cylinder, and the crankshaft completes 2 revolutions for each thermodynamic cycle. So these engines are called 4-stroke internal combustion engine. Later on, we are going to look into how it is look like. I think better we try to understand the process. Initially, both the intake and the exhaust valve are closed, and the piston is at its lowest position. Okay, BDC. I think you can recap back what is BDC. And during the compression stroke, the piston moves upward, compressing the air-fuel mixture. Right? Shortly before the piston reaches its highest position, the TDC, the spark plug fires and mixture ignites, increasing the pressure and temperature of the system. So the high pressure gases force the piston down, which in turn causes the crankshaft to rotate, producing a useful work output during the expansion or the power stroke. Right? So that's what happened in this particular movement, compression stroke. The piston move upward, and then there's a spark there to ignite, right? And then the exhaust stroke movement and the intake stroke movement. Okay, so let us just try to read through. And toward the end of the expansion stroke, the exhaust valve open and the combustion gases that are above the atmospheric pressure rush out of the cylinder through the open exhaust valve on top of the cylinder. So this process is called exhaust blowdown, and most combustion gases leave the cylinder by the time the piston reaches BDC, and the cylinder is still filled by the exhaust gas at the lower pressure at BDC. So now the piston moves upward one more time, which purging the exhaust gas through the exhaust valve, and down a second time, drawing a fresh air-fuel mixture through the intake valve. And notice that the pressure in the cylinder is slightly above the atmospheric value during the exhaust stroke and slightly below during the intake stroke as shown over here, right? So the top four figure here, actual four-stroke spark ignition engine, and this is the PV diagram for the actual four-stroke spark ignition engine, and for the ideal Otto cycle, being simplified, right? Instead of having complicated spark plug and exhaust gas in and out, we just simplify it, just having Q in and Q out, right? So let us read through it. The resulting cycle, which closely resembles the actual operating condition, is the ideal Otto cycle. It consists of four internally reversible processes. 1 and 2 is isentropic compression. 2 and 3, process of constant volume heat addition. Process 3 and 4, isentropic expansion. And 4 and 1, constant volume heat rejection. And you can see 2 and 3 Q in, 4 and 1 Q out. Process 1 and 2 is isentropic compression, 3 and 4 isentropic expansion, right? Okay, so this is the TS diagram for the Otto cycle, 1, 2, 3, 4, where the volume is constant for process 2 to 3 and 4 to 1. You can see here for the Otto cycle that includes intake and exhaust stroke for the PV diagram. Okay, process 1, 2, 3, 4, and 1. Right, so it has already been highlighted in the earlier figure. Right, so we can observe from this particular figure 918, thermal efficiency of the ideal Otto cycle as a function of the compression ratio. The compression ratio K equal to 1.4, right? Compression ratio at specific heat ratio of 1.4. This is for air. Okay, compression ratio, the symbol is R. This K is the specific heat ratio. We can observe here that the thermal efficiency curve is rather steep at lower compression. At the lower compression over here, this part, the thermal efficiency is very steep. Okay, but it flattens out. It flattens out over here, and where you have a higher compression ratio, and this is a range of a typical compression ratio for gasoline engine at about 8. Therefore, the increase in thermal efficiency with the compression ratio is not as pronounced at high compression ratio. Alright? The second parameter which affects the thermal efficiency of an ideal Otto cycle is the specific heat ratio. The specific heat ratio K or gamma, and for a given compression ratio, an ideal Otto cycle using a monatomic gas such as argon or helium at the K equal to 1.667, argon or helium, if you refer back to the table A2 earlier in our session before the break, okay, you can see the different values of K for different gases. Okay, these particular gases for monatomic gas, as the working fluid will have the highest thermal efficiency. You can see here, the higher the value for the specific ratio, it will have the higher thermal efficiency for Otto cycle. Thus, the thermal efficiency for ideal Otto cycle will decreases as the molecules of the working fluid get larger. Higher, larger molecule, you will have a lower thermal efficiency. At the room temperature, okay, we know that specific heat ratio for air is 1.4, carbon dioxide is 1.3, and ethane is 1.2, and the working fluid in actual engines contains larger molecules such as carbon dioxide, and the specific heat ratio decreases with temperature, which is one of the reasons that the actual cycle have lower thermal efficiencies than the ideal Otto cycle. So the thermal efficiency of actual spark ignition engine range from about 25 to 30% only. Let us look into one example related to Otto cycle. We have an Otto cycle having a compression ratio of 8. At the beginning of the compression process, air is at 100 kilopascal and 17 degrees Celsius, having 800 kilojoule per kilogram of heat is transferred to the air during the constant volume heat addition process. Okay, so those are the conditions. Accounting for the variation of specific heat of air with temperature, we have to determine the maximum temperature and pressure that occur during the cycle. What is the maximum temperature? And then the net work output, the W net, the thermal efficiency, the zeta TH, and the MEP, mean effective pressure for the cycle. You also have to determine the power output from the cycle in kilowatt for an engine speed of 4,000 RPM. You have to assume that this cycle is operated on an engine that has 4 cylinders with total displacement volume of 1.6 liters. So you'll be given all the information needed for you to come up with the answers. For the solution, an ideal Otto cycle is considered over here. The maximum temperature and pressure, the network output, the thermal efficiency, the mean effective pressure, and the power output for a given engine speed are to be determined. What are the assumptions? Number one, the air standard assumptions are applicable. Right? So this is the standard answer. And then kinetic and potential energy changes are negligible as well. And the third one, variation of specific heat with temperature is to be accounted for. So the value of K in this particular case has to be accounted in order for us to answer the question. PV diagram of an ideal Otto cycle is described here in figure 920. Right? So you have the process of compression, isentropic compression, 1 to 2, 2 to 3, where you have heat addition, 3 to 4, isentropic expansion, and 4 to 1, the expel of the heat from the system. Okay, so the volume also being given over here. We note that the air contained in the cylinder form a closed system. Right? Maximum temperature and pressure in Otto cycle occur at the end of the constant volume heat addition process at state number 3. But first we need to determine the temperature and pressure of air at the end of the isentropic compression. Right? At the state number 2 using data from table A17. Right? The next slide I have a snapshot of table A17 from the thermodynamics book. We have the information of T1, 290 Kelvin. We need to read the value of internal energy U1 and VR1. Okay? So from the table A17, ideal gas properties of air, you know the temperature at 290 Kelvin. You have the value of the enthalpy, the PR, the Prandtl number, okay, the internal energy, and then the VR, and then the S value. Okay, so you can then get the corresponding value out. For process 1, 2, isentropic compression of an ideal gas, right? So you then want to find what is the given the compression value R is 8 in this particular case, and we know VR1 676.1 at 290 Kelvin. Then you have the value for VR2 84.51. From there, you can get the corresponding value of T2. What is the at this value from the table? You can get the value of T2 652.4 Kelvin, internal energy 472.11 kilojoule per kilogram using the same table, right? And input into the equation PV over T for 1 and 2. You can then rearrange it to get the value of pressure at station number 2 correspond to 1799.7 kilopascal. Right? Continue to that. Process 2 to 3 constant volume heat addition. You know Q in equal to U3 minus U1. Right? You have already the value of Q in. You need to find what is the value of U3. You already know the value of U2 from the previous answer. This is from the previous answer. The moment you get it wrong, you will also get the answer for U3 wrong. Okay, so that's where you can then read from U3 1275.11 kilojoule per kilogram from the table. You read back what is the corresponding value for the temperature and the value of VR3. Okay, then you can get, using the same approach, you can then get the pressure at station number T, which corresponds to 4.345 megapascal. Right, the second section B, the net work output for the cycle is determined either by finding the boundary pressure interchange of volume dV, work involved in each process by integration, and adding them or by finding the net heat transfer that is equivalent to the net work done during the cycle. We take the second approach and the later approach. We want to find the net work done. However, first we need to find the integral energy of air at state 4. Process 3-4, we know it is an isentropic expansion of an ideal gas. So we apply the same condition, right? Where we know R equal to 8, and you can get the value of VR4. From VR4, 48.864, you read from the table P4 correspond to 795.6 Kelvin. U4 internal energy equal to 588.74 kilojoule per kilogram. Process 1, constant volume heat rejection, right? So you know the value of U1, you know already the value of U4, then you can get the rejected heat 381.83 kilojoule per kilogram. From there you can get the work done, and the net work done, which is equal to the net output, the net heat input, which is Q in minus Q out, okay, which is equal to the 418.17 kilojoule per kilogram. Thermal efficiency, from there, W net over Q in, you get 52.3%. Alright, so all of this is the ability to read from the table A17 just now, from one process to another process to another process. So I would strongly suggest for you to go through this example again and try to make sense of the steps and answers obtained. Under the cold air standard assumptions, constant specific heat values at room temperature, the thermal efficiency would be from equation 98, right, for Otto cycle, right? So you put inside the numbers, and you will get it to be 56.8 5%, which is considerably different from the value obtained earlier. We have 52.3, but over here we have 56.5% for the thermal efficiency for Otto cycle. Therefore, care should be exercised in utilizing the cold air standards assumptions. For the mean effective pressure, which is determined from equation line 4 of the MEP, so you can then put inside the values, V1 over equal to RT1 over P1. You have all the values already. You get V1 equal to 0.8 to the meter cubic per kilogram. Okay. Thus, for the MEP itself, right, you get 574 kilopascal, and the total air mass taken by all 4 cylinders were, when they are charged, is the mass equal to VD over V1, and you have the volume for the cylinders divided by V1 equal to 0.00192 kilogram. Right? The net work produced by the cycle is then can be calculated. Right? We have already found earlier the net work 418.17. You times the mass, you will get the total net work for the cycle. So that is the net work produced per thermodynamic cycle 0.807037 kilojoule per cycle. Noting that there are 2 revolutions per thermodynamic cycle, right? In a 4-stroke engine, or in the ideal Otto cycle, including intake and exhaust stroke. The power produced is basically W net times N watt, the revolution per minute, okay, divided by the number of rev per cycle, okay, then you get the answer to become the power of the engine is 26.8 kilowatt. Okay. Note, if you analyze a 2-stroke engine operating on ideal Otto cycle with the same values, the power output would be calculated as follows. We get 53.6 kilowatt, and this is 1 revolution in 1 thermodynamic 2-stroke cycle. For the previous one is we are taking the 2 revolution per thermodynamic cycle, because in a 4-stroke engine we have 2 revolution per cycle. That's why the value is half from the one that being obtained over here. Okay, so the last part of the session today is looking into another type of cycle, which is the diesel cycle, which is the ideal cycle for compression ignition engine. Okay. In a combustion engine, CI engine, also known as diesel engine, the air is compressed to a temperature that is above the auto ignition temperature of the fuel, and combustion starts on contact as the fuel is injected into this hot air. Right? So air fuel mixture over here. For gasoline engine, we have a spark plug. For diesel engine, we have a fuel injector. Which injected fuel into the air, and then it becomes air mixture. Right? So the spark plug is replaced by fuel injector for the diesel engine comfort. The air standard diesel cycle is the ideal cycle that approximates diesel combustion engine. So we also have the PV diagram and the TS diagram for the diesel engine. So basically process 1 to 2 isentropic compression, 1 to 2 in the TS diagram isentropic compression, 2 to 3 it is the constant pressure heat addition, right, at constant pressure, 2 to 3 at constant pressure, 3 to 4 isentropic expansion, 3 to 4 isentropic expansion, and finally 4 to 1 constant volume heat rejection. V is constant over here. Right. What are the thermal efficiency for a diesel cycle? Zeta TH diesel equal to the work net work done divided by the total amount of heat into the system equal to 1 minus Q out over Q in. Right? So now to find Q in and Q out, we have to apply first law closed system to process 2-3, where the pressure is constant. The energy into the system minus the energy out is equal to the total change in the energy. Then you can write down Q net 2-3 process minus work done net by 2-3 process equal to the change in internal energy from process 2 to 3, and you can then simplify it to become the pressure times the volume difference between 3 and 2. Okay, remember, from 2 to 3, pressure is constant, the volume is not constant. Thus, for constant specific heat, constant Cp, right, you can rewritten Q net to 3, right, as delta U to 3 plus pressure at 2 times the volume difference between 3 and 2, right, and then you can replace it using the MC theta, MCV times the temperature difference, plus MR times temperature difference. So you can simplify it as the amount of heat into the system at 2-3 equal to the mass times the specific heat capacity at constant pressure times the temperature difference between 3 and 2. Right? Apply first law closed system to process 4-1, where in this case the volume is constant. So you know the volume is constant, and you apply the same thing, E in minus E out equal to delta E. So you have Q net for 1 minus W net for 1 equal to delta U for 1. Replacing everything, you get W net for 1 equal to 0. Equate it into 0. Right? Thus, for constant specific heat, right, you can then rewritten the same thing, the same approach as Q in just now, right, in terms of the constant volume instead of constant pressure. Thermal efficiency finally becomes zeta TH diesel, and you can rearrange this until you get the value of this expression. And zeta TH diesel equal to 1 minus 1 over K. 1 over K basically is the specific heat ratio. K is specific heat ratio, right? And then you have all the values to be included. Okay. Thus, to continue, the PV over 3 for volume, P3 times V3 over T3 equal to V2 over T2, where we know the at constant pressure P3 equal to P2. So we have another terminology here. RC is called the cut-off ratio, which is defined as V3 over V2, volume at 3 over volume at 2, and is a measure of the duration of heat addition at constant pressure. And since the fuel is injected directly into the cylinder, the cut-off ratio can be related to the number of degrees that the crank will during the fuel injection into the cylinder. Thus, P4 over T4 equal to P1 V1 T1 for the process 4 T1, where now the volume is the same, V4 equal to V1. Okay, and then you can rearrange that cancel out V4 and V1, so you can get P4 over T1 equal to P4 over V1. We recall the process 1, 2, and 3, 4 are isentropic. So P1 V1 to the power of the specific heat ratio equal to P2 V2 to the power of specific heat ratio K. And the same for 4 and 3. So we know V4 equal to V1 and P3 equal to P2. We divide the second equation by the first equation and obtain this expression, right, of the cut-off ratio. Okay, therefore, for thermal efficiency for diesel engine can be rewritten as the component of the specific heat ratio. The cut-off ratio are specific heat ratio for the system, right? In a situation when the cut-off ratio is more than 1 or a fixed R, the thermal efficiency for the diesel is less than thermal efficiency for the Otto cycle. However, since the R for diesel is more than R for the Otto cycle, the thermal efficiency for the diesel will be greater than thermal efficiency of the Otto cycle. So this figure 2.3 shows thermal efficiency of the idle diesel cycle as a function of compression as well as the cut-off ratio. Cut-off ratio, the RC, compression is given as R. So is given in this particular graph. Let us look into one example. Bear in mind, this example using the English unit. And somehow in this particular textbook, they provide an English unit, so I do not have any time to change it into the SI unit. Let us go through this. An idle diesel cycle with air as the working fluid has a compression ratio of 18. Is given compression ratio R to be equal to 18. Cut-off ratio of 2, the RC equal to 2, R equal to 18. At the beginning of the compression process, the working fluid is given at 14.7 PSIA at a temperature of 80 degree Fahrenheit and a volume of 117 inches cube. Utilizing the cold air standard assumption, determine the temperature and pressure of air at the end of each process, the net work output and the thermal efficiency, and finally the MEP, mean effective pressure. So as a solution, an idle cycle is considered, the temperature and pressure at the end of each process, the network output, the thermal efficiency, and the mean effective pressure are to be determined. We can assume that the cold air standard assumptions are applicable, and thus air are assumed to have constant specific heat at room temperature. And of course, kinetic and potential energy changes are negligible in this example. Properties of air is taken from table A2EA. A2A is the SI unit. A2EA is the English unit. Somehow, this example being given in English unit. Right? The gas constant of air at being given here is 0.304 PSIA feet, cubic feet over pound m dot Rankine, the temperature. And other properties at room temperature are given as follows and taken from this table A to EA. Analysis. The PV diagram of idle diesel cycle described is shown in figure 9 to 5. The PV diagram for idle cycle is discussed in this example. We note that the air contained in the cylinder form a closed system. A closed system meaning that it is reversible 1 to 2, 2 to 3, 3 to 4, 4 to 1, and it is continued to 1 to 2 again. So the temperature and pressure values at the end of each process can be determined by utilizing the ideal gas isentropic relation, process 1, 2, and 3 to 4. Okay, take note on the volume, the volume for each cases over here. We need to first determine the volume at the each end of each process from the definition of the compression ratio and the cut-off ratio. So we know that V2, R equal to V1 over V2. Rearrange that, you will get V2 value, right? And RC equal to V2 over V3. Rearrange that, you get V3 equal to 13 cubic inch, and V4 equal to V1 equal to 117 cubic inch. Okay, for process 1 to 2, isentropic compression of an ideal gas with constant specific heat. So you know the expression is, this is the expression for the isentropic compression of ideal gas. Just the value are in English unit, and this time around, right? So you get the value for temperature, T2, and the pressure at the corresponding station, for station number 2. Right, for process 2-3, constant pressure heat addition to an ideal gas, PV over P, okay, for 2, which is equal to 3, right, because the pressure is the same, 841 psia, you then get the value for T3, which is equal to 3,432 Rankine. For process 3-4, isentropic expansion of an ideal gas at constant specific heat, okay, the same formula being used for 2 to 3. Okay, now you can apply, 1 to 2, apply it for 3 to 4 expansion, you will get the value for T4 and P4, right? Then the network for the cycle is equivalent to the net heat transfer, so you can rewrite, find the value for the mass of air first. Okay? P equal to PV equal to MRT, right? So you can rearrange to get the M value, which is 0.00498 pound. Process 2-3 is a constant pressure heat addition process for which the boundary work and change in internal energy terms can be combined into change in enthalpy. So that's where you get the Q in equal to 2.051 BTU. I'm not really familiar with the English unit, but you can actually convert it back into the SI unit. Process 4-1 is a constant volume heat rejection. It involves no work interaction, and the amount of heat rejected is as follows. And earlier we get the Q in, then now we get the Q out, so that we can get the work net work that in from the system, which is equal to 1.297 BTU. So finally, you will get the thermal efficiency, which becomes 63.2%. Right? So the thermal efficiency for diesel under coal air standard assumption could also be determined from equation 912. Equation 912, you can get the same expression. For the MEP, mean effective pressure, from equation 94, right, you get 110 psia. Note that a constant pressure of 110 psia during the power stroke would produce the same net work output as the entire diesel cycle. Okay, so that's what we have for today. We have already looked into 3.1 until 3.6. We shall continue for the remaining topic on gas power cycle, which include Stirling and Ericsson cycle, another two type of cycle that are very relevant before we jump into the Brayton cycle for gas turbine engine. And this is from 3.8 onwards, more applicable to our aircraft propulsion subject. The previous topic from 3.1 until 3.7 is just to understand what are the fundamental and basis of gas power cycle before we move into the jet propulsion cycle. So we will continue on Monday and to cover the topic on Stirling and Ericsson cycle, Brayton cycle with regeneration, and then Brayton cycle with intercooling, reheating, and regeneration. Finally, we'll also look into ideal jet propulsion cycle before we complete our gas power cycle topic on the subtopic on second law analysis of gas power cycle. All right. So I would strongly advise you to try to go through a few examples that I have already shared in this particular session, so that you try to make sense on how to go about it, what are the assumptions need to be made, right? And then how to read the PV diagram and the TS diagram, right? And to make sense on where is the direction of the PV diagram and TS diagram, right? The process of going from stage 1 to 2, 2 to 3, 3 to 4, and 4 to 1, and how to read the values from the corresponding table, right? It's not that much. It's just in terms of familiarity, right? When you go through it again, probably you will get more insights in terms of where the numbers are coming from. Okay, so thank you for your attention. I believe it is quite a lengthy exercise for this 2 hours session, and we'll try to continue again on Monday. If you have questions, probably I would strongly suggest that you try to go through the slide again and as well as the example given, so that you know what. And if you still have questions, you can ask me on Monday. All right. So